the areas of the circumscribed triangles and they added them up. And they found out that as the number of choppings gets greater and greater, the sum of the areas of these triangles are less than the sum of the areas of the circumscribed triangles. And in fact, they're getting closer and closer to each other. In fact, you can take, I don't want to do this because it's really beyond, it's really taking more time than we really need. It's a historical remark. But what you do is you say that 1/2 R times L1 plus L2 plus L2 to the n, okay, or 1/2, actually it's this base here. It's not R, it should be, I should really use, this is B1 here. So this is B1, this is B2. So it's 1/2 B1 times L1 plus 1/2 B2 times L2, so on and so forth. This is always less than pi r squared, and it's less than 1/2 R times L1 plus 1/2 R times L2 plus so on. So in fact, the method of exhaustion says, hey, if I take these inscribed triangles, I get a number less than pi r squared. And if take the circumscribed, I get something bigger than pi r squared. Now, it turns out that as your choppings get, you can see that as the number of choppings gets finer and finer, okay, more and more choppings, and gets larger and larger, you can prove, and the Greeks proved that this number gets closer and closer to this number. So this number exists, and it's getting closer and closer to these numbers. In other words, they all exist, and they're getting, it's just like stepping, like I did the other day, just a hopscotch. At each stage, these two numbers, one to the right, one to the left, are getting closer and closer to each other, and this number is caught in between. So this has to be the area, because it's caught in between something which is bigger than the number and something which is less than the number, and these things are squeezing in on it. So this number, it existed and it's caught in between two areas, which are getting closer and closer to each other. So this is called the principle of exhaustion. It's actually the principle of exhaustion, and correct me if I'm wrong, was an argument by contradiction.
Well, that's right. Let me just clarify it a little. In fact, what they showed is that the term you have on the left, if you took any number smaller than pi r squared, right, any number smaller than that, they showed that eventually the number on the left would exceed that.
If the area was less.
If the area was less, they should, well, if you took any number smaller than C, 1/2 R times C, okay, or pi r squared, tell me, then you took any number less than that, they showed that the
eventually
on
this
the
would
left,
exceed it.
That would eventually exceed it, all right? And so if one assumed that that is not the area, then it's either less or it's more. If it's less, then you get a contradiction, because the area of the circle is
the area of the enclosed region has to be greater than
the area of the inside triangles, but that number could be made to exceed anything that's smaller than pi r squared.
Right.
So that gives you a contradiction if you assume it's smaller than pi r squared.
Right.
And then if it's larger than pi over squared, you can show that the number on the right for large enough subdivisions is going to be smaller than any number that's bigger than pi r squared. So once again, you get a contradiction.
Right. So it has to be pi r squared.
So they argued twice by contradiction.
They argued by twice using the following fact. Another intuitive principle of area, which I didn't write down. If A is contained in B, then the area of A is less than the area of what? Of B. So they argue by contradiction, but by arguing by contradiction, you miss the connection between between area and no. That's the problem. So they never could fill the holes in the number system, and as I said, that wasn't done until the end of the 19th century. Now, there are other logical problems about what number was. that the Greeks, and I'm going to talk about that, why the Greeks, from another point of view, couldn't resolve that issue. So we'll talk about that maybe after the, it's now time for our break. The lunch lady is surely